Welcome back. In the last class, we started learning about node analysis using KCL or Kirchhoff's current law to simplify electrical circuits. And we already know that KCL is one of the important methods in the world of electrical circuits. As I promised that I will be covering about this law in two classes, and this is our second class where we will be solving or simplifying a few more electrical circuits using KCL. So let's get started.
Now we are talking about that node, and with that node two or more than two branches are connected. So first we have to know what is node. Node is a junction where two or more than two branches of that particular electrical network are connected. Now node can be, as we know, node can be of different types. If it is if in that node only two branches are connected, then that node is called simple node. And in case of simple node, so there will be only two branches which will be connected with that node. So here A, this node is a simple node where only these two resistors are connected, and these two resistors are connected in series. So whatever current will be flowing through the first resistor, the same current will be flowing through the second resistor. So here at a simple node, no current gets divided, current remains same. But if we have a node where two or more than two branches are connected of that network, then that node is called principal node. And at principal node, as I said, that there will be more than two branches which will be connected. So at principal node, current does not remain same through all the branches or components of the network. Current gets divided. That is the difference between simple node and principal node. Now there will be a node when we will be doing node analysis in an electrical network. There will be a node which will be connected to the ground. So that particular node is called reference node, and always the potential of that node is 0 volt. So though there more than two branches will be connected to that node, but since we have connected that node to ground, so that node will always at ground potential. The potential will be 0 volt, and that particular node is referred as a reference node. So next we will see and we will simplify another electrical network based on node analysis. Now this is an electrical network where we need to find out the current value through 1 kilo ohm resistor. Now here in this electrical network, as we can see, there are three resistors, there are two voltage sources, and there are two current sources. Now if we think of applying mesh analysis, then here we have one mesh, two and three meshes, and from there we can find out three equations. Now if we want to apply node analysis, then we have to identify first that how many principal nodes are there. As we can see, there are one node here, principal node, where this resistor and this current source, they are connected. So this is a principal node. Three branches are connected. Here we have another principal node where this resistor, this voltage source, and this current source, these three branches are connected. So we have two principal nodes, and at the bottom of the circuit again we have another node or junction where we have 1, 2, and then 3, and this resistor also. These four components are connected. So in this circuit we have three principal nodes, and if we want to apply node analysis, then as we know that one of the principal nodes will be connected to ground. Now suppose if we choose this node to be connected to the ground, then the potential of this node will be 0 volt. So this node is our reference node. Then other two principal nodes, let's mark as A, and let's mark the other principal node as B. So these two principal nodes. Now if we apply node analysis, and if we form the node equations, then from these two nodes we will be having two node equations. So number of node equations are here less than the mesh equations. So we will apply node analysis method here. Now this circuit can be solved in two ways by applying node analysis or KCL. First, we will see, uh, we will apply the concept of source transformation, and then we will simplify the same circuit without applying the concept of source transformation. So in the first approach, we will first transform the sources. So as we can see here in this at the left side of the circuit, we have a voltage source here, and with that voltage source, this 4 kilo ohm resistor is connected in series with that voltage source. So what we can do is, since if we apply KCL or node analysis, if the all the energy sources are in the form of current sources, then that makes our job easier. So since this voltage source and this resistor are connected in series, so easily we can transform this voltage source and we can convert this voltage source to an equivalent current source. Now for that we have to apply Ohm's law. So the current value for this voltage source will be, the voltage value is 12 volt and the resistance value is 4, so it will be 3 ampere. And for if we come to the right side of the circuit, here also we can see that we have a voltage source here, and with that voltage source we have a resistor which is connected in series. So we can also easily transform this voltage source to an equivalent current source. Now here also the current value we can find out by using Ohm's law, and this time the current value will be 8, which is the voltage value, divided by 4, so it will be 2 ampere. And in that transform circuit, with, as we know that with those current sources, these resistances will be connected in parallel. So after transformation, let's redraw the circuit and then we will apply node analysis. So if we redraw the circuit, it will look like this. So this voltage source has been transformed into this current source, which is okay, this was 4 kilo ohm, so it will be 4 into 10 to the power 3, so it will be 3 milliampere. 3 into 10 to the power minus 3, so it will be 3 milliampere. And similarly, it was 8 volt and the resistance value was 4 kilo ohm, so 4 into 10 to the power 3, so it will be again 2 milliampere. So 2 into 10 to the power minus 3 ampere, that means 2 milliampere. So here in this transform circuit, we have now this current source in place of this voltage source, and since the polarity wise, this is the positive terminal and this is the negative terminal of the voltage source, so as we know, the current will leave the positive terminal of that voltage source. The direction of the current will be this, downwards. So that's why the direction of the current source is downwards. In this direction the current is flowing in the from the current source. So 3 milliampere that we have already got from Ohm's law. And as I said, this 4 kilo ohm resistor will be connected in parallel with the transformed current source. That's how it is connected now. And then this current source, as it was connected in the original circuit, that resistor, and this current source, that is we have drawn as it was connected in the original circuit. Now the right side of the circuit, here this voltage source has been transformed into a current source, and since this side is the, so the left side we have the positive terminal for this voltage source, and right side we have, at the right side we have the negative terminal. That means current is flowing this way with respect to the this voltage source. That means the current is flowing, if we vertically think, then current is flowing upward. So that's why the direction of this current source is upward for this current source, and the value wise it is 2 milliampere that we have already got by applying Ohm's law. And again this resistor will be connected in parallel with this current source, so that's how it is connected. Now in this circuit we, as we can see, we have again this node where 1 2 3 4, this 4 components are connected, and at this node again 1 2 3 4, these 4 components are connected, and at this node and node at the bottom we have 1 2 3 4 5 6 components are connected. So all these 3 nodes are principal nodes. Now again we will be connecting this node to the ground, and this we will make as our reference node. Then at rest of the nodes, we will be applying node analysis. So for doing that, we have already identified the principal nodes. We have chosen our reference node, and next we will assume the potential at rest of the principal nodes. So at this node, let's assume the potential is VA, and at this node, let's assume the potential is VB. Now we will apply the concept of KCL and we will form the node equations. Now at this node, at node A, if we apply KCL, then we know that the summation of all the incoming currents will be equal to summation of all the outgoing currents with respect to that node. Now with respect to this node, this current source, the direction is given. It's with respect to this node, it is incoming current, and with respect to this node, this current source, this current is outgoing current. And for rest two branches where we have registers, we don't know what will be the direction of the current. So we will assume as if the currents are leaving that node. So if we assume that the currents are leaving, then accordingly we will form the node equation. So first we will consider what are the currents that are incoming with respect to that node. So moving towards that node, with respect to the 1, 2, 3, all these three currents are outgoing currents. We have only one current, which is incoming current. So let's write the value of that current 2. So it is 2 into 10 to the power minus 3, and then we have the currents, this 3 milliampere. So this is 3 into 10 to the power minus 3. This is outgoing current, and through this resistor we have assumed that the current is outgoing. So it is moving from this A point to the reference node. That means as per the direction of the current that we have assumed, this point A is at higher potential and this point is at lower potential. So when we will find out the current value, we know that as per Ohm's law, it is the potential difference between 2 points divided by the resistance between that path, resistance of that path. So if we want to find out the current value, then we have to first find out or consider the potential difference of that path, and that is potential of the point A, which is VA, minus potential of point the reference node, which is 0. So this is potential difference divided by the resistance value, which is 4K. So it is 4 into 10 to the power 3. Then we have another outgoing current. For that, this is at higher potential and this will be at lower potential if we go by the direction of the current. So it will be written as VA minus VB, which will be the potential difference of this between these 2 points, divided by the resistance value 1 into 10 to the power 3. So this is our first equation, node equation. Now if we rearrange, then we will get 2 into 10 to the power minus 3, and this will be 3 into 10 to the power minus 3, plus it will be VA divided by 4, and we have in the denominator 10 to the power 3. So if we take that to the numerator, then it will become 10 to the power minus 3. Then plus we have VA minus VB and divided by 1, and again we have 10 to the power 3 at the denominator. Then if we take to the numerator, then it will become 10 to the power minus 3. Now as we can see that in this equation, with each term we have this 10 to the power minus 3, that value or that factor common. So they will cancel each other if we take this 10 to the power minus 3, that factor common, and if we divide by if we divide both the sides of that equation by 10 to the power minus 3, then we will not have this 10 to the power minus 3 factor anymore in that equation. So minus 4. So this is our first equation that we have formed with respect to node 1, or after applying KCL at node 1. Now next step will be application of KCL at node B. So at node B, as we can see, we have again four branches which are connected to that node, and here the direction of this current is already given, which is going towards that node, and with respect to this node this is incoming current, and also for this current source also this is incoming current with respect to this node, and for the other two resistors the current directions are not given. So here also we will assume that with respect to this node the current are leaving that node, and current are outward current with respect to these two registers. So, and one more thing that we can here consider is to simplify our equation, that for these two current sources the current values are again in milliampere, and the resistance values are also like before, they are in kilo ohm in that unit. So as we have seen in the first equation, that this finally we got on the both sides of that equation 10 to the power minus 3 factor because of this milliampere current and kilo ohm resistance. So this time, to simplify or to save time or to simplify our calculation, we will not consider that 10 to the power minus 3 or 10 to the power plus 3 in case of resistance from the beginning. So what we will write is here at node B, if we apply KCL, then this is our incoming current. So we will write that incoming current value, that is 1, and this is incoming current, so that is 2. So 1 plus 2, this is the summation of incoming currents, and that will be summation of the outgoing currents. Now for this resistor, through this resistor, the current that will be flowing, we have assumed that the current will be outgoing. So this, and again with respect to node P, through this resistor current will be outgoing. So for this resistor the current value can be written as VB minus 0, the potential of the reference node, divided by 4, plus for this resistor the current value will be the potential difference between these 2 points, and with respect to the current direction that we have assumed this time, this point B will be at higher potential and point A will be at lower potential. So current value will be found out this way: VB minus VA, this is the potential difference of those 2 points, and divided by the resistance value, and which is 1. So this time we have not considered the 10 to the power minus 3 and 10 to the power plus 3, those values from the beginning, as we know the reason. Now if we simplify further, then it will be 3, and then it will be VB by 4 plus VB minus VA. Now if we simplify further, this will become, the equation will be this side 12, and that will be equal to VB, and here it will be multiplied by 4, this VB minus VA. So we can write minus 4VA plus 5VB, that will be equal to 12, and this is our second equation. And what was our first equation? First equation was 5BA minus 4B, and this time it is 4BA and 5BB. So what we need to do is, if we multiply this equation by 5, then this equation will become minus 20VA plus 25VB, and that will be equal to 60. And if we multiply the first equation by, we have 20 VA, so this time 5 VA, so if we multiply by 4, then it will become plus 20 VA plus, we had 4 VB minus 4 VB, so it will be minus 16 VB, and that was equal to minus 4, so it will be minus 16, or we can say VB will be 44 divided by 9, which will be equal to 4.89 volt. So this is the potential of point B. What we need to find out finally is the current through 1 kilo ohm resistor. So we have to find out the potential of point A also. The equation was minus 4VA plus 5VB, and that was equal to 12. So if we write this way, that if we take 4BA on the other side, so it will be 4BA and it will be 5BB minus 12. So what we can see here, that the potential of point B has higher value, which is 4.89, and potential of point A that has lower value, and that is 3.11. That means potential point B is at higher potential and point A is at lower potential. That means current will be flowing in this circuit or through this 1 kilo ohm resistor. Current will be flowing from point B to point A, and if we want to find out the current value which is flowing through this 1 kilo ohm resistor, then it will be again can easily be found out by using Ohm's law, and that will be VB minus VA divided by the resistance value, which is 1 kilo ohm. This time we want to know the actual value, so we have to consider the kilo ohm, that whole resistance value. So 1 into 10 to the power 3 and this value. So finally, if we simplify this value, this will be 1.78 milliampere. So this is our answer. So current which is flowing through this 1 kilo ohm, that value is 1.78 milliampere, and that is flowing from point B to point A. Now this same circuit we will simplify by using node analysis, and this time in the second approach we will not apply source transformation concept. So we have the same circuit here and we will not apply source transformation method here. But as we can see here, we have three principal nodes A, B, and the node that we have at the bottom that we are taking as a reference node. So apart from that, if we exclude that node, then we have two principal nodes. So we will have two node equations here. So let's apply the concept of KCL at node A. So here again we can see the current of this current source. It is with respect to this node, it is incoming, that current direction. And for these two resistors, since their current directions are not given, so if we assume that the currents are leaving this node, then if we apply KCL, we will be having this type of equation. So this is incoming current, 2 milliampere, so 2 into 10 to the power minus 3, and then that will be equal to the summation of all the outgoing currents. So here this is VA, this is VB, the potentials. So through this resistor, if we want to find out the current value, then this time it will be VA minus VB, as the current direction we have assumed is outgoing with respect to this node. So A will be at high potential, B will be at lower potential. So VA minus VB is the potential difference of that between these 2 points, and this is the resistance value. And for this path, for this branch, the potential difference will be of this point, this is VA. Then at as the voltage value of this voltage source is 12 volt, and this is the negative terminal, and here we have the positive terminal, so we have to consider this voltage value as the negative voltage. And since we are finding out the potential difference, so it will be VA minus of, and this value itself is negative since the negative terminal is at this side. So it will be VA minus of minus 12, and potential of this point is 0. So it will be 0 divided by the resistance value, which is 4 kilo ohm. So 4 into 10 to the power 3. So it will be VA minus VB divided by 10 to the power 3 plus it will be VA plus 12 divided by 4 into 10 to the power 3. Now if we simplify further, is 3, and we already had on the left side 2 into 10 to the power minus 3. So 10 to the power minus 3, this factor is common, so we can cancel from the both sides. So this equation will become, if 2 which is equal to VA minus VB plus VA plus 12 divided by 4. The equation as 5VA minus 4VB, which will be equal to, if we take 12 on the other side, that will be equal to minus 4. So this is our first equation. 5VA minus 4VB is equal to minus 4. This equation we have derived, we have formed for from node A, and this is the equation that we have got for the same circuit when we applied source transformation method. That was 5BA minus 4BB, which was equal to minus 4. So we have derived, we have formed the same equation from the same node. Now at node B, if we apply KCL, let's see what equation we may form. So at node B, if we apply KCL, we can see here we have three branches which are connected. Now this current source, the direction of the current is incoming with respect to this node, and for the other two branches, since their current directions are not given, so we will be again assuming that with respect to node B, the currents are leaving that node. So first we will consider all the incoming currents, which is this time only one. So 1 into 10 to the power minus 3, 1 millihenry, and other two currents are outgoing current. So for this resistor, the current value will be the potential difference between those 2 points, VB minus VA, with respect to the direction of current that we assume, and it will be 1 into 10 to the power 3. And then for the other path, other branch, the potential difference will be this time VB minus, since the positive terminal here at this side, so this value of this voltage source will be taken as positive value, so it will be plus 8 volt. So this time VB, then we have to subtract this this potential, this voltage value, and this time it is positive, so VB minus 8, and then the potential of this point, and which is at ground potential, so VB minus 8 minus 0 divided by the resistance value, which is 4 kilo ohms, so 4 into 10 to the power 3. Next we have to simplify this, minus 3, so 10 to the power minus 3, this factor is common, so we can cancel from both the sides. Now if we further simplify this equation, it will be 4, that will be equal to 4VB minus 4VA, then plus VB minus 8. If we simplify further, then it will be minus 4VA, then we have 5VB, and then if we take this minus 8 on the other side, this will become 12. So this is our second equation. So let's check whether we have formed this, we have got the same equation or not for the second from the second node. So minus 4VA plus 5BV, and that is equal to 12. So this was the equation that we derived for the first approach, minus 4BA plus 5BB, and that is equal to 12. So if the equations are same, then finally the values, the potentials of this point B and point A, that will be also same. And when we will find out the current value through this 1 kilo ohm resistor, that value will be same as we have already derived for the first approach. So this is the application of node analysis or KCL, and this time we have not used any source transformation method. Now let's simplify another circuit using node analysis method. Here what we need to find out is, we need to find out the potential of point A and point B. Okay, let's mark this as point A, and the other side of the register as point B. So we have to finally find out the potentials of these 2 points, and this circuit may look bit complex. Now what we can see here is we have 3 loops, one here, and here. So from this circuit or electrical network, we can form 3 mesh equations. Now if we consider the principal nodes, we can see clearly that we have one node here where we have 1, 2, 3 and 4 branches are connected. So this is one principal node, and this node are same. And if we consider this node, then we can see that here also we have 1, 2, 3, three branches which are connected. So this is also our principal node. And then we have another node here where we have more than two branches, 1, 2 and 3 branches are connected. So this node is also principal node. Now what we will do is, we have already identified our principal nodes and we have to connect one of the nodes to the ground. So since we want to find out the potentials of these two nodes, so we will connect the last node, the third node, to the ground. So as we will make this node as our reference node, so potential of this node will be 0 volt. So what we will do next is we will apply the concept of KCL at node A and node B. Now when we will apply KCL at node A, again the concept is same. The summation of incoming currents first we have to consider, and that will be equal to summation of all the outgoing currents. Now for this branch, as we can see, there are three components which are connected in series: this resistor, this voltage source, and there is also a current source whose value is 5 ampere. So since these three components are connected in series, and we know in a series circuit, the current remains same through all the components which are connected in series. The current value, the same current flows. So if the value of this current source is 5 ampere, that means we can say that through this 2 ohm resistor, or through the whole branch or through the whole path, this 5 ampere current is flowing. That means, and the current direction, since it is given, this is upward with respect to this path. So if we consider, if the whole direction of this current path, then the current is basically leaving this node. So with respect to this node, the direction of current of this branch is outgoing current. Now come to the other branches which are connected to this node. For this resistor, the current direction is not mentioned, so we will assume that the current is leaving this node. So this is one. And then for this path also, there are two components, resistor and voltage source. They are connected in series, and the current direction is not mentioned, so we will assume that the current is leaving that node. And for this branch, there is a current source whose current direction is given, and that is incoming. With respect to this node, this is incoming current. So if we now now look at this node, finally what we can see is, with respect to this node, 1, 2, 3, these three are outgoing currents and there is one incoming current. So first we will write the incoming current value, which is 5, and 5 milliampere, not 5 milliampere, this time it is ampere, so it is 5, and that will be equal to the summation of all the outgoing currents. So let's consider one by one. So let's assume the potential of this node is VA and potential of this node is VV. So if we consider the current value, then it will be with respect to the direction of this current, the potential difference will be VA minus VB, and that will be divided by the resistance value, which is 4 ohm. So this is the current value. And then if we consider the current of this path, this branch, then it will be, potential of this point is VA, and then we have a voltage source. The positive terminal is connected to this point, so it will be taken as positive voltage. So since we are finding out the potential difference, so it will be VA minus 10, and then potential of this point is 0, so minus 0, divided by the resistance value, which is 2. And then this is another outgoing current, so this is 5 plus 5, so this 5, we have 5 on both the sides, so we can cancel both the 5. And then if we simplify further, it will be VA minus VB plus 2VA minus 20, and that will be equal to, on this side we have 0, so it will be 0 into 4, so it will be 0. So final equation will be 2VA plus VA, which is 3VA, and then we have one VB minus VB here, and we have minus 20 here. So if we take on the other side, that will become plus 20, and this is our first equation. Now at node B, if we apply KCL, let's see what equation we may form. At node B, we have three branches which are connected. So again, for this branch, with respect to this node, if we assume the current direction is this, current is leaving that node, and this current is entering this node. This is incoming current, this is outgoing current, and for this branch also, if we assume that this current is leaving or outgoing current, then incoming current is 5 amperes. So let's write that 5 first, and then summation of the outgoing currents. So this time it will be VB minus VA by 4. VB minus VA divided by 4, and current of this path, or this current which is flowing through this resistor, will be VB, and potential of this point is 0, so it will be VB minus 0 divided by 2. 2 ohm is the resistance value. So let's simplify further. It will be VA minus VB minus VA plus 2VB divided by 4. Now in the first equation we have 3VA, here we have minus VA. So if we multiply second equation by 3, we'll have another equation which is minus 3VA, then plus 9VB, and that will be equal to 60. So if we simplify these two equations, so minus 3VA plus 9VB, and that is equal to 60. So VB will be equal to 80 divided by 8, so it will be 10 volt. Now from this equation, if we find out VA, VA will be 3VB minus 20. VA will be 3VA, and if we take 20 on the right side, then 3VA minus 20. So VB itself is 10 volts, so it will be 30 minus 20, that means 10 volt. Now what we wanted to find out is what are the voltages of node A and B in the following circuit. So VA we have found out, and that is 10 volt, and also we have found out VB, which is also 10 volt. So this is the solution. So this is the end of this.